Welcome to Derectronic, where we experiment, learn, and build with electronics. What you see right here on the breadboard is a 4-bit full adder circuit using a 74LS283 that you see right here. A 74LS283 integrated circuit like this one takes two binary numbers as input of 4 bits each. These inputs will be facilitated by the DIP switches you see here at the upper right hand portion of the circuit. And it outputs a 4-bit sum, which will be shown on the blue LEDs that you see here at the lower right hand portion of the circuit. Being a full adder, the 74LS283 can also handle a carry bit, and this carry bit output will be shown through this white LED that you see right here. The 74LS283 integrated circuit has 16 pins, with the half moon notch located on this side of the circuit. Pin 1 is here at the lower left hand, followed by pin 2, 3, 4, 5, 6, with pin 8 here at the lower right hand portion of the IC. Pin 9 will be here at the upper right hand portion of the IC, with 10, 11, 12, 13, 14, 15, 16 going to the left, being pin 16 shown here at the upper left hand portion of the IC. Ground pin for the 74LS283 is pin 8, while the VCC pin or the supply voltage pin is pin number 16. As you can see in the circuit right now, I connected pin 8 to the blue side of the lower power rail, which I will be using for my ground, and I connected pin 16 to the red side of the upper power rail, which I will later use for my VCC. You could also see from here that pin 7 is also connected to ground. Now, pin 7, if you consult the data sheet for the 74LS283, is the carry out pin. Now, the carry out pin in this particular demo will not be used, and it needs to be tied low. So this is the reason why I connected the pin 7 of this 74LS283 to ground, similar to what I did to pin number 8. As mentioned earlier, the input to our 4-bit full adder circuit will be facilitated through the DIP switches you see here at the upper right hand portion of the breadboard. Now, these two DIP switches are set up here in the circuit as follows. The on side of the DIP switches, as you can see here at the top portion, is actually tied high to VCC, while the off side of the DIP switches are tied to ground through these 8 2 kilo ohm resistors, which I'm using as pull down resistors for this circuit. For purposes of reference later on, I'm labeling the first DIP switch as switch A and the second DIP switch as switch B. Now, what I will be using as the most significant bit for switch A will be pin 1 of switch A, and my least significant bit would be pin number 4. For switch B, it's the same thing. I'm using pin 1 of switch B as my most significant bit, and pin 4 will be my least significant bit. Now, for easier reference, I will just refer to these switches or these particular pins as A1 here, A2, A3, A4 for switch A, for each pin of switch A, and for the pins of switch B to be B1, B2, B3, and B4, with A1 and B1 being the most significant bits, and A4 and B4 being the least significant bits. I also mentioned earlier that a 74LS283 integrated circuit like this one outputs a 4-bit sum with a carry bit. Now, the carry bit and the 4-bit sum will be illustrated in this circuit through this white LED that you see here on the left-hand side and these 4 blue LEDs. As you can see in the circuit here, okay, I have 5 resistors, each 330 ohms, tied to the anode of each of these LEDs connected to ground. These 330 ohm resistors, 5 330 ohm resistors are acting as current limiting resistors for each of the LEDs. For purposes of reference, okay, I will name the LEDs you see here as follows. The white LED here will be LED 1. The first blue LED here would be LED 2. The next one will be LED 3. The next blue LED will be LED 4. And the last blue LED here that you see here on the right-hand side will be LED number 5. Now, the LED 1 or this white LED will actually be connected to pin number 9 of the 74LS283. Pin number 9 is the carry-in pin of the 74LS283. I mentioned earlier that the 74LS283 also has a carry-out pin, which is pin number 7, which you tied to ground. So you can see in the circuit. Now, if you're wondering where pins 7 and 9 are actually being used for 74LS283s, okay, we use these pins in the 74LS283 if we are cascading several 74LS283 together in one circuit. Let us now connect the input part of the circuit to our 74LS283. Now, the jumper wires we will be using needs to be connected between the DIP switches and the pull-down resistors here. Given the setup I have here, I have two choices. I can connect the jumper wires here on this section directly below the DIP switches, or here in this area a little bit nearer to the pull-down resistors. Now, what I will be doing, I will be connecting the wires through here, this area, a little bit near to the pull-down resistors. I will start with switch B first. Based on the schematic diagram shown on the inset, okay, the pin B4 is connected to pin number 6 of the 74LS283. B3 is to be connected. B3 is to be connected to pin number 2 of the 74LS286. Pin number 2 is there. B2, on the other hand, is to be connected to pin number 15 of the 74LS286. 283, I'm sorry. 74LS286, pin 15. Okay, let's connect to pin 15 there. And B1 is to be connected to pin number 11, the 74LS283. Let's get this one connected. Okay, pin 11, 74LS283. There. Okay, there. Now, for switch A, okay, let's do the connection of one by one, starting with A4. A4, okay, A4, let me use another wire for this one. Let me use a orange wire. Okay, A4 is to be connected to pin number 5, the 74LS283, so that will be pin number 5. Okay, this one here, there. A3 is to be connected to pin number 3 of the 74LS283, so pin 3. Let's connect it to pin number 3 here, there. Okay, A2, connect to A2. A2 is to be connected to pin number 14 of the 74LS283. That's pin number 14 there. And A1 here is to be connected to pin number 12 of the 74LS283. There. Now, that completes the connection of the input section of our 4-bit full adder circuit. Let us now connect the output section to our 74LS283. As mentioned earlier, the output section will be the 5 LEDs here. I forgot to mention earlier that our most significant bin, by the way, would be LED 1, the white LED here. Our least significant bit would be the last blue LED here, as you see here on the right. So when we read the output, we read it from left to right, similar to what we're going to be doing for the inputs wherein the 4-bit binary digits inputs will be read also from left to right for each of the switches, switch A and switch B. Now, the connections of the output are as follows. Okay. Now, actually, the white LED, as I mentioned earlier, is already connected to pin number 9, which is the requirement here. As you can see here, through this gray jumper wire, it's connected. The anode of the white LED is already connected to pin number 9. Now, the anodes of the other LEDs are to be connected as follows. For the first blue LED, LED 2, this is to be connected. The anode of this blue LED needs to be connected to pin number 10. Pin number 10. There. Now, for LED 3, the anode of LED 3 is to be connected to pin number 13 of our 74LS2A3. Pin number 13. Okay, let me just connect it properly here. Pin number 13. There. Okay. LED 3. LED 4. The third LED here. The anode of LED 4 needs to be connected to pin number 1 of the 74LS2A3. So all the way to pin number 1 here. Down. Like that. There. And the last LED here, there on the right, LED number 4, LED 5, sorry. The last blue LED is to be connected to pin number 4 of the 74LS2A3. Now, we be connected to pin number 4. There. Now, with that, we've completed the connection of the output section now of our full adder circuit. To test the circuit, I've just connected the power rails to my power supply. The positive supply is connected here on the red side of the top power rail, and the ground is connected here on the blue side of the bottom power rail. Now, let's test it by putting some inputs. What I will do, I will switch on. Now, notice that the all 4 switches for both switch A and switch B, all 4 pins for switch A's and switches A and B, I've put down to off. Now, I'm going to switch on the switches here for both switches for A and B one by one, and see if I'm going to get the correct output. I'll start with switch B here, going to the left. Then I'm going to traverse to switch A, also going to the left. Let's do it one by one. So, for instance, 0 for switch A and 1 for switch B will give me 0 plus 1, output is 1. Correct. Okay. Now, if I put out the next switch after that, that will be a 3. So what I have here is 0 for switch A and 3 for switch B will be equal to 3, which is correct. Okay. And the output you can see here, 0, 0, 0, 1, 1. I have a 3 there in binary. Then if I pull up this switch here, the next one on switch B, there, that's a 7 now. Okay, so we have 0 plus 7, 0 for switch A and 7 for switch B, and I have an output of 7, 0, 0, 1, 1, 1. Then let's change the value for switch B again by putting high the last switch there, B1. So 1, 1, 1, 4 ones is actually 15. The binary representation for 15. So I have here 0 plus 15, in which case the output will be 15. So you can see right here, 0, 1, 1, 1, 1. That's 15. So that's still correct. Now, let me now put an input now put a value for switch A. I'm going to start with the LSB first. So which is the 1, okay? So, what do I have here right now, okay? For switch A, I have 1. For switch B, I have 15. So, I have 1 plus 15, which is 16. Now, see right here, this is 16, okay? With the carry bit on and all the 4 blue LEDs off, okay? That's 1, 0, 0, 0, 0. That's 16 in binary. Okay, now, let's have another input for switch B. So, I'm gonna switch on the second one. B3 pin, okay, there. So now switch A. Switch A now has 3, 0, 1, 1, 0, 0, 1, 1, that's 3. And I've got 1, 1, 1, 1 on switch B. So that's actually 3 plus 15, which will give me 18. Now, you can see here on the output, okay, 1, 0, 0, 1, 0. That's 18 in binary. 1, 0, 0, 1, 0. 18 in binary. Now, let's change the value of switch A again by turning on A2, like that. Okay, now, what do I have on switch A now? I've got 7 now, okay? That's 0, 1, 1, 1. That's the binary representation for 7. And I have 15 for switch B. So I have 7 plus 15, that's 22. Let's take a look at the output. I've got 1, 0, 1, 1, 0. 1, 0, 1, 1, 0, okay, is the binary representation of 22, which is actually 7 plus 15, 22. This is 22 in binary, 1, 0, 1, 1, 0. Now, let's switch on the last here, okay? A1, switch A1. Now, as I've said earlier, 1, 1, 1, 1 is 15. So what I have here, 15 for switch A and 15 also for switch B. So I've got 15 plus 15, that's 30. Let's take a look at the output. Okay, what I see on the output, 1, 1, 1, 1, and 0 for the LSB. So I have 1, 1, 1, 1, 0. That's 30 in binary. So you can see right here, our circuit is working perfectly. With that, I would like to bring to a close this video on full adder. And again, as always, I would like to encourage everybody to keep experimenting, keep learning, and I hope to see you all next time here in Derektronic.